Ever get that feeling, when you're looking at pictures of deep space? Like those incredible shots from Hubble, all those galaxies just scattered across the blackness, and you think, man, the space between them is just dot empty.
Yeah, it's a pretty common misconception, actually.
Really?
Yeah, we call it the intergalactic medium, or IGM for short.
Yeah.
And yeah, it's about as close to a perfect vacuum as you can get, but insignificant. No way. Not at all.
Okay, so our source material for this deep dive is called The Emptiest Places. And I gotta say, that title, at first, it did kind of sound, I don't know, dismissive. Like we're talking about leftover cosmic crumbs here.
Right, right.
Like, what is it? Just a few atoms per cubic centimeter?
Yeah, incredibly diffuse.
Mm-hmm.
But like you said, looks can be deceiving.
Yeah. As we were digging into this, I was blown away by how wrong that initial impression can be.
It's amazing, isn't it? This thin gruel, as the article calls it, it actually holds the keys to some of the biggest mysteries in astronomy.
No kidding. We're talking about how galaxies form, how the universe changes over time.
The very structure of the cosmos, even.
Exactly. So today we're doing a deep dive into that thin gruel, the IGM, using the emptiest places as our guide.
And it's a fascinating story, believe me.
Oh, I bet. It's like, how do we even study something that's practically invisible? Which, by the way, is something we're going to unpack today, along with, I don't want to give too much away.
Let's just say there's some serious cosmic detective work involved.
Oh, yeah. Invisible forces shaping the universe, galactic winds.
It's incredible how astronomers have pieced this all together, using these faint whispers of light and energy. It really is like a giant puzzle.
Speaking of puzzle pieces, the Emptiest Places article, it lays out 4 big clues that have been, well, instrumental in unlocking the secrets of the IGM.
It's true. Each one gives us a different piece of the story.
Okay, so clue number 1, we've got the cosmic microwave background radiation, which is essentially, what, a baby picture of the universe, right?
Exactly. This faint afterglow of the Big Bang. It gives us a glimpse into the IGM's earliest days, back when he was transitioning from this hot, ionized state to a cooler, neutral one.
Okay, so I'm picturing, like, the universe is a pot of soup, right?
Okay.
It starts out incredibly hot, everything's all mixed up and crazy, and then it starts to cool down and things begin to separate. That's kind of like what was happening in the early universe, yeah.
It's a good analogy. And just like with your soup, things can get pretty interesting as the universe cools.
But then things get weird again.
That's where our second clue comes in. Quasars.
Oh, yeah. Quasars, those things are insane, like unbelievably bright.
They're some of the most luminous objects in the universe.
So are they kind of like cosmic flashlights, shining their light across, what was it, billions of light years?
Exactly. And as that light travels through the IGM, it carries with it these fingerprints of everything it's encountered along the way.
Okay, hold on. Back up a bit. How do we go from flashlight beams to, like, actual information about what the IGM is made of?
So this is where it gets really cool. Astronomers, they use a technique called spectroscopy, where they basically take the light from a quasar and they split it up into its different wavelength, like a prism. And when they do this, they see something really remarkable. This forest of dark lines. Each of these lines represents a cloud of hydrogen gas. But here's the kicker. Each cloud is at a different distance from us. So it's like we're looking at snapshots of the IGM at different points in cosmic history.
So it's kind of like taking core samples of the IGM, but with light instead of drills.
Exactly. Like a cosmic core sample. And those core samples, they reveal something totally unexpected.
What's that?
Those lines, they were too distinct, too sharp. See, if the hydrogen in the IGM was mostly neutral, like we originally thought, we should have seen this broad absorption trough, not this forest of lines.
Okay.
This meant something had reionized the hydrogen early on. And that discovery, let me tell you, it completely changed our understanding of the early universe.
Okay, so we've got the cosmic microwave background for the really, really old days, then quasars giving us snapshots throughout time. What else are we using to piece together this puzzle?
So our third big clue, it comes from something completely different. X-ray emissions.
Okay, X-rays, like at the doctor's office?
Well, kind of. But in this case, we're talking about X-rays coming from some of the most massive structures in the universe.
Yeah.
Galaxy clusters.
Galaxy clusters, those giant groups of galaxies all huddled together.
Exactly. And it turns out these clusters, they shine brightly in X-rays.
Really? Like giant cosmic lighthouses, but in X-rays instead of visible light.
That's a great way to put it. And you know what's even cooler? The X-rays tell us something really important about the IGM that's trapped inside these clusters. It's insanely hot.
How hot are we talking here?
Tens of millions of degrees.
Whoa. Okay, wait, something's not adding up here. Even the most intense stars, they don't get that hot, right?
That's right. Gravity alone, it couldn't heat the IgM up that much. Which leads us to our fourth and final clue. The one that helps explain this whole mystery. Magnetic fields.
Hold on, so the IgM, this thin gruel, it's also magnetized.
You got it. It's not just a vast emptiness. It's this dynamic, magnetized environment.
Okay, now we're really diving into the deep end here. Empty really doesn't seem to cover it at all. So these magnetic fields, can we actually see them or?
We can't see them directly, no, but we can observe their effects.
Ah, I see. Like how they influence the stuff around them.
Exactly. They affect how charged particles move within the IgM, and that plays a big role in those ridiculously high temperatures we were just talking about.
Okay, so to recap, we've got these 4 big clues about the IgM. The cosmic microwave background, quasars, X-ray emissions, and now magnetic fields.
Right. And each one gives us a little piece of the puzzle.
But how do we go from these individual pieces to actually understanding the IgM's like epic journey through time?
Well, that's where the real detective work begins. By combining all these observations with theoretical models. Astronomers have actually been able to piece together a pretty amazing story. It's a story of, well, really dramatic transformations that ultimately shaped the universe we see today.
And the article, it actually lays out this story in 3 acts, right? Almost like a cosmic play. I like it.
Yeah. Act 1 is called recombination.
Okay.
Remember that baby picture of the universe that we get from the cosmic microwave background? Well, that picture, it captures the moment when the universe had cooled down enough for protons and electrons to, well, recombine.
To form neutral hydrogen, right?
Exactly. It's like after the Big Bang, the universe finally took a deep breath and just started to settle down a bit.
Okay, so Act 1 is all about things cooling off, calming down. What happens next in this cosmic drama?
Act 2 is where things get really interesting. Reionization. Remember those telltale lines in the quasar spectra, the ones that told us the hydrogen in the IgM was ionized?
Right. Right, the Lyman alpha forest. Like a giant neon sign flashing, something reionized the universe.
Exactly. See, that discovery, it meant that something had to be pumping energy back into the IgM, basically stripping electrons off those neutral hydrogen atoms. The big question was, what could possibly generate that much energy, enough to reionize the entire universe?
That's the million-dollar question, isn't it?
It was a real head-scratcher. And it's where those incredible first stars and galaxies, they enter the picture.
Okay.
Astronomers, they believe that the intense radiation from these early objects, maybe even those powerful jets blasting out of quasars, that's what provided the energy needed for reionization.
So not only did these early stars and galaxies like light up the universe, but they also totally changed the properties of the IgM itself. And that set the stage for, well, everything we see today. It's amazing. But there's one more act, right?
Oh, yeah.
The grand finale.
Act 3, heating. We already talked about those crazy hot galaxy clusters, how they're extreme temperatures they couldn't explain by gravity alone. Well, this is where things get even more explosive.
Okay, you're talking about supernovae now, right?
You got it.
Those massive stars that die in these huge explosions.
And they release just insane amounts of energy. Imagine these supernovae as like cosmic furnaces, blasting out shockwaves and energy that just rip through the IgM.
Wow, so they heated it up.
Oh, they did more than just heat it up. They enriched it.
Wait, back up a sec. Enriched it with what? I thought the IgM was basically just hydrogen and helium, right?
It is, mostly.
Yeah.
But those supernovae, they created heavier elements.
Okay.
Elements like carbon, oxygen,
Yeah.
even iron. The very building blocks of planets and life itself and all those elements, they were blasted out into the IgM.
Wow.
They became part of its makeup.
Okay, so we've got these supernovae going off, spewing out all this heavy stuff into the IgM. But where's it all going? Does it just drift around aimlessly? So we've got these supernovae going off, spewing out all this heavy stuff into the IgM. But where is it all going? Does it just drift around aimlessly?
None at all. This is where we get to one of the most, I think, dynamic phenomena in the universe.
Yeah.
Galactic wind.
Galactic winds. Okay, come on. Now you're just messing with me.
I wish I were. These winds, they're very real. And they're driven by those supernova explosions we were talking about.
Yeah,
So
okay.
picture this. You got a galaxy, right? Full of stars and gas.
Okay.
Now imagine supernovae going off, kaboom, releasing just ridiculous amounts of energy.
Yeah.
And that energy, it heats up all the gas around it, creates this pressure so intense that it basically blasts the gas outwards.
Out of the galaxy.
Out of the galaxy in these massive outflows. Like, if you'll excuse the analogy, a galactic sneeze.
A galactic sneeze. Okay, I kind of love it. But seriously, how powerful are these sneezes? Like, Can they really affect anything outside their own galaxy?
Well, absolutely. They're powerful enough to actually influence the formation of other galaxies.
Ooh.
See, the IGM, it's not just a passive backdrop. It's in constant interaction with these galaxies and these
Ugh.
galactic winds. They can actually strip a galaxy of its gas.
Really?
Oh, yeah, especially smaller galaxies, the ones that aren't as gravitationally bound as like,
So they're just going about their business, trying to grow and evolve, and then bam, galactic smeeze comes along and blows it all away.
pretty much.
That seems kind of rude, don't you think?
Well, the universe can be a harsh place. But you know what's really cool? The article talks about these observations that astronomers have made. They've actually seen evidence of these galactic winds shaping how galaxies form.
Wait, hold on. How do you even observe a galactic wind? It's not like you can see it with a telescope.
You're right, you can't see them directly,
Right.
but we can use light to detect them.
Okay.
So they use this technique called spectroscopy. Basically, they study the light coming from these galaxies.
Spectroscopy, like splitting the light into different wavelengths.
Exactly, like
Yeah.
shining it through a prism.
Okay, yeah, I remember that from like high school physics or something. But how does that help you see a galactic wind?
Because the light, it carries clues, you know?
Yeah.
It can tell us if something is moving towards us or away from us. Like, think about an ambulance siren. It sounds higher pitched when it's coming towards you and lower pitched when it's moving away.
Right.
It's called the Doppler effect.
Right. Okay, so you can do that with light too.
Exactly. So what astronomers found was that the light coming from the heavy elements in these galactic winds, it was slightly blue shifted,
Blue shifted, meaning.
meaning it was moving towards us. But the light from the rest of the galaxy, the hydrogen gas, it was red shifted, meaning it was moving away.
Oh, wow. So by analyzing those shifts in the light, they could actually, what, map out the galactic wind?
That's exactly it. They can
Yeah.
figure out its shape, its speed. It's really incredible.
It's like a cosmic radar gun, but for light. That's amazing. But I gotta say, this is a lot to wrap my head around. Galactic winds, supernovae, all this stuff happening in the IGM. What's the takeaway here? Why should we care about cosmic sneezes?
Because it shows this amazing interconnectedness, between galaxies and the IGM. It's this giant feedback loop.
A feedback loop? How so?
Well, you have these supernovae that explode within galaxies.
Yeah.
Those create the galactic winds, which then blow material out into the IGM.
Right.
And that material, it influences the formation of the next generation of stars and galaxies.
Mhm.
So it's this beautiful cosmic dance, with galaxies and the IGM pushing and pulling on each other.
It's mind-blowing to think how much is going on in the seemingly empty space between galaxies. And speaking of which, the article mentions some new observations that are pretty wild. Something about a hot gas halo around our own Milky Way galaxy.
Yes. It seems our Milky Way might be sporting a massive halo of this superheated gas, kind of like a mini version of those hot galaxy clusters we were talking about.
You mean we're living in a giant cosmic hot tub?
Well, I don't know about a hot tub, but you get the idea. Astronomers are calling it a corona.
Corona. Like the sun's corona.
Exactly. And just like with the sun's corona, we're not entirely sure where it came from or what it means. Could be leftover stuff from when the Milky Way first formed, or maybe it's material being pulled in from the surrounding IGM.
So even in our own galactic backyard, there's still so much we don't know. It's pretty humbling, honestly.
It really is. But, that's what makes studying the universe so exciting. There's always something new to discover.
Absolutely. Well, I think we've gone from thinking of the intergalactic medium as this vast, empty void to, well, anything but. It's dynamic, it's essential.
And maybe even a little bit explosive.
Yeah, just a tad. And the best part is, we're only just scratching the surface. I mean, who knows what other secrets are hidden within the emptiness of space?
It makes you wonder, doesn't it? What else is out there just waiting to be discovered?
It really does. And on that note, I think it's time for us to step out of the cosmic hot tub for now. But this is definitely one deep dive we'll be revisiting soon, that's for sure.
I'm looking forward to it.
Until next time, everyone, keep looking up. And never underestimate the power of those seemingly empty spaces.